the subject I'd like to talk about is the ground state for relativistic molecules in the Dirac-Fock model. So let me start with very... I cannot change my... okay. Yeah, I can do it with the mouse. Okay, so let me start with very basic remarks in the non-relativistic case. And also I'm going to introduce notations that I will use throughout the talk. So I call phi the Coulomb potential generated by a nuclear density, a nuclear charge density nu. Okay, this charge density is supposed to be fixed. I am not interested in optimizing the geometry of the molecule. And I call capital Z the total charge of this nuclear density. Capital N will be the number of electrons that live in the vicinity of this nuclei. Okay, so in the special case, so here for the moment I am non-relativistic. So I'm looking at the Schrödinger equation. And for just one electron, as you know, the ground state is a wave functions normalized in L2, which minimizes the Schrödinger energy. Okay, so integral of psi multiplied by the Schrödinger operator applied to psi. And this minimization problem also, of course, has an associated Euler-Lagrange equation, which is just the eigenvalue equation. And so the minimizer is an eigenstate of the Schrödinger operator with eigenvalue, the eigenvalue being the smallest possible eigenvalue of this operator. Okay, so now if we have n electrons, the object we have to look at is a wave function depending on all the spin and space coordinates of our n electrons, and of course we have to impose an antisymmetry condition. Okay, so if you exchange two electronic coordinates, you change the sign of psi. And this means, from a mathematical viewpoint, that psi lives in the antisymmetrized tensor product of the monoelectronic, of n copies of the monoelectronic Hilbert space. And the ground state, exactly as for n equal 1, is a minimizer of a quadratic form associated with the Hamiltonian. But now the Hamiltonian is the n-body Hamiltonian. And as you know, the main problem in quantum chemistry is that this Hamiltonian, of course, lives in a space which is much too big, and so this makes numerics quite hard. The Hartree-Fock approximation consists in instead of working in the very big space, in this very big antisymmetrized tensor product, in working with particular wave functions living in that space, which are tensor products themselves of monoelectronic wave functions. And these are the famous Slater determinants. So now the energy it only depends on these n monoelectronic wave functions that constitute the Slater determinant, and this makes the problem much easier to discretize. So the Hartree-Fock ground state is just a minimizer of the Hartree-Fock functional, which is a restriction of the quadratic form we had before to the set of these Slater determinants. The explicit form of this Hartree-Fock energy is quite easy to write as a function of the density matrix associated to our n monoelectronic wave functions. So this density matrix is just the projector on the n-dimensional space generated by these monoelectronic wave functions. So its integral kernel takes the form I wrote here in the first line. To this integral kernel is associated a charge density. Well, of course, if it's an electronic charge density, I should put a minus sign in front of it, but we forget that here. And so this charge density is just the diagonal part, or more precisely, if we have spin, it should be the trace over C2 of the diagonal part, because the diagonal part is a 2x2 matrix. Anyway, so we have this charge density, and associated with this charge density, we have this energy, which is exactly the Hartree-Fock energy. So first, you have a term which is the term where interactions between electrons are not taken into account. So it's the trace of minus Laplacian plus phi times gamma. So minus Laplacian accounts for the kinetic energy, and phi accounts for the electrostatic energy of the electrons in the field of the nuclei. And then you have a quadratic term, which represents the interaction electrostatic energy of the electronic cloud. Okay, so you have a first term, which is the repulsion energy, rho of x times rho of y, and then you have the exchange term, minus gamma, which squared, which takes into account the antisymmetry of the wave function. Okay, so now the ground state is just a minimizer. The Hartree-Fock ground state is just a minimizer of this energy. And it was a very important remark made by Lieb around at the beginning of the 80s, that in fact, instead of just minimizing over the set of projectors of rank n, you can minimize on a larger set, which is a convex envelope of the set of projectors. And so this larger set is defined by these constraints. So gamma should be self-adjoint. Gamma square should be less or equal to gamma in the sense of self-adjoint matrices. Or if equivalently, gamma should be between 0 and the identity. Or equivalently, all the eigenvalues of gamma should be between 0 and 1. All these defines your convex constraints. And then the last convex constraint is, is that the trace of gamma should be less or equal to n. And what Lieb proved is that for n less or equal to z, you can minimize under this constraint the Hartree-Fock energy, and you find that the minimizer, in fact, saturates the constraints. So it is an extremal point of the convex set defined by the constraints. In other words, it is exactly a projector of rank n. And that's exactly what was the purpose. The purpose was to recover a projector of rank n. And this projector of rank n, in fact, solves the Euler-Lagrange equation, which can be seen as a self-consistent equation, the one that is solved in most quantum chemistry codes. So gamma should be the spectral projector associated with a mean field operator H gamma, and it should be a spectral projector associated to an interval minus infinity mu, where mu is a chemical potential. Mu is not fixed in advance, but it is such that the mean field operator H gamma has exactly n eigenvalue below mu. Okay? And so gamma should be of the form which is here in the first line. It should be a projector of rank n, and the psi case should be the wave functions that constitute the ground state Slater determinant. Okay, so just a word on the mean field Hamiltonian. It's just made of kinetic energy plus potential phi plus Well, the mean field potential generated by the electronic cloud. Okay. So, of course, this is a highly nonlinear equation because here you have a projector associated with an operator, which itself depends on gamma. And so you can think of the problem of the ground state as either being a fixed point problem by just looking at the equation or being an optimization problem. Okay. So now let me go to relativistic quantum mechanics. So first, just a word about the importance of relativistic quantum mechanics in quantum chemistry. If you look at atoms with charge at least 26 and higher, you find that you cannot neglect a relativistic effect. Okay, because if you do that, then you get wrong prediction. Okay, so sorry. So how do you go from non-relativistic to relativistic quantum mechanics? Well, you have to introduce the Dirac operator. And here I give you the definition of the free Dirac operator, so without interaction. It is a first-order differential operator with coefficients alpha k's that are matrices. There is also a coefficient in front of the constant term, which is beta. And in fact, alpha k's and beta should satisfy anti-commutation rules. These rules are such that the Dirac operator should have a square equal to minus c square Laplacian plus m2c4, which is the, quantum mechanical analog of the relativistic relation between energy and momentum. So you find that the simplest solution are 4 by 4 matrices, and these are the Dirac matrices. And the operator you get in this way has a spectrum which is rather easy to compute by going to the Fourier domain. And you find that it has two parts, a negative part, minus infinity minus mc square, and a positive part, mc square infinity. Of course, nobody has ever seen negative energy electrons. And so this negative spectrum is a problem. This problem was solved by Dirac in his famous picture of the Dirac sea. So Dirac's idea was to consider that the vacuum, in fact, consists of an infinity of virtual electrons occupying each negative energy state of the Dirac operator. So if you go to, if you look at the consequences of that assumption, well, when you don't have any interaction, you don't see the electrons, you don't feel them, because they are virtual and occupy states that are invariant under translation. But if you add an external field, then the virtual electrons can react, and that creates effects that are well understood now in the context of quantum electrodynamics. These effects are first vacuum polarization, and second, the creation of electron-positron pairs in very high and very strong fields. So in this talk, I am not going to be... Sorry?
Yeah, ask a question. Is the operator D0 that you presented is the only operator that satisfies D0 squared equal to minus Laplacian plus the constant?
No, it's not, but it's not. But if you add the constraint that it should be a local operator, and by local operator, I mean a differential operator, not an integral differential operator. Then you don't have much choice. You see that it has to be a first order differential operator, and so you just write it as in the form which is here in blue, and you consider your coefficients as unknown, and now you have constraints which are the anti-commutation constraints exactly coming from the relation d square equal minus Laplacian blah blah blah. And if you want the operator to be self-adjoint, then essentially, and if you look for matrices alpha k's of the smallest possible dimension, then yes, it's the only one, up to change of coordinates in C4.
So either we impose locality and then we have this problem of negative spectrum, or we
a locality plus this relation imposes negative spectrum. Yeah. Because otherwise, you see, there's another solution. You go to the Fourier domain, and then minus Laplacian plus mc squared gives you a symbol, p squared plus m squared, okay? And you take the square root. And then you go back to direct space, but it's not local. Okay, so where was I? Yes, I was here. So what I was saying is that I am not going to consider vacuum polarization. I'm not going to consider electron-positron pairs in this talk. Okay, so what we do is something very naive, which was done, very naive but very useful, which was done by Swirls in 1935. I think Swirls was a PhD student, no, a postdoc student of Hartree, if I remember well. And what she did, she just replaced the Laplacian of the Schrödinger operator by the free Dirac operator in the Hartree-Fock equations. Okay? And so let me remind you of the Hartree-Fock equations. They are here, okay, in this very condensed form. You ask gamma to be a spectral projector up to chemical potential of a mean field operator. Okay, so you're going to try to do the same, but you replace the Laplacian by Dirac. But now, since Dirac has a negative spectrum, and since you don't want negative energy electrons, you cannot take minus infinity mu. You have to take 0 mu, let's say. So that's the equation here. So gamma, the n-body, sorry, the density matrix corresponding to our n electron state should be, and chi means 1 here, sorry, should be the spectral projector associated to the interval of eigenvalue 0 mu of the mean field operator d gamma, where the mean field operator d gamma is really like the mean field operator for Hartree-Fock, but with Laplacian replaced by Dirac. Okay? And here, sorry?
May I ask another question? Is it equivalent to taking Slater determinants, injecting it in the some energy, and looking at this equation as Euler-Lagrange equation?
Yes, it's the next slide.
Right.
You are completely right. There is an energy hidden here. But I first presented the Euler equation because really that's how it's explained in Swirl's paper. She just looks at the equation as a self-consistent equation, really in the spirit of what is done in quantum chemistry very, very often. Okay, you look at this as a fixed point problem. So that's what's really the way she derived the equations, just replacing the Laplacian by the Dirac operator d0. Just a word about...
sorry, just one more question. The characteristic function is between 0 and mu, not minus 1 and mu, because you could...
Yeah, you can. Okay, you are right. I could take minus 1 and mu, but... well, normally there are no negative eigenvalues. There are no eigenvalues between minus 1 and 0. Sometimes there could be by accident, so it's better to do 0 mu. Okay? But of course, this is only meaningful if the charge of the nuclei is not too big. But the charge of the nuclei is never too big if you look at existing nuclei. Now, if you invent nuclei with a very, very high Z, you might have a problem. You might have eigenvalues crossing the spectral gap. Okay? So this is for, let's say, physically existing atoms. Okay, so yeah, and so just a word about physical constants. There was no alpha in the Hartree-Fock. Okay, let me look at the Hartree-Fock here. There was no alpha in front of the interaction potentials and in front of phi. Or if you prefer, our units here were such that the square of the charge of the electron divided by 4 pi epsilon naught, it was equal to 1. But we cannot do that in relativistic quantum mechanics. We cannot do that because D0 is a first order operator as well as the Coulomb potential. So there is a dimensionless constant that has to appear, which is this alpha here. And this alpha has a physical value which is about 1 over 137. All these constants have been put to 1. Okay, so we'll want to look at this equation. And so to answer a question which has been asked before, there is a Dirac-Fock energy, which is, well, essentially the Hartree-Fock energy with D0 instead of the Laplacian. So it looks very much the same. So you can say that the equation here is the Euler-Lagrange equation for this energy. So the Dirac-Fock projector, the solution gamma, is a critical point or stationary point, sometimes it's called like that, of this Dirac-Fock energy under the constraints that gamma should be a projector of rank n. So it's a critical point, but not a minimizer because D0 is not bounded below. So if you try to minimize this Dirac-Fock energy, you just get minus infinity. Okay. Defining a ground state in particular is a problem. So let me just explain what happens for n equal 1. For n equal 1, it's not so hard. You don't have any interaction, of course, and you just have D0 plus the electrostatic energy due to the nucleus. And so you look for an eigenvalue and an eigenvector psi. So the eigenvalue is lambda. And well, if you want to have a ground state, you want lambda to be positive and as small as possible in the set of positive eigenvalues. So that's what I call this lambda 1. Okay. So that's going to be a kind of ground state. Okay, that's the best we can say. Well, even from a numerical point of view, this can create some difficulties when you discretize such a problem because this lambda 1 is not the smallest eigenvalue. Below lambda 1, there are infinitely many elements of the spectrum, and so this might cause spectral pollution. But okay, I don't want to go into this too much. Let me just mention a min-max characterization of lambda 1, which was introduced by Thalmann and Data and Devaya in the 80s. The goal precisely was to avoid this problem of, to solve this problem of spectral pollution. And the idea is very simple. You take your wave function. So I remind you, it has 4 components because our matrices alpha, k, and beta are 4x4 matrices. And now you split it into its first component, its first 2 components, and its last 2 components. So the first 2 components form a vector phi, the last 2 a vector chi. And what you do is, for fixed phi, you maximize over chi the Rayleigh quotient. And then, once you've done this maximization, you minimize over the upper spinor. Okay, and Thalmann gave convincing arguments and also made some computations showing that this principle works. Now, if you want to prove rigorously that it works at the level of functional analysis, you need to do some more work. And this was done in the last 20 years. Anyway, the problem we want to look at is not this one, it's the one with n larger than or equal to 2. And so you want to find critical points of the Dirac-Fock function. But let me say something. When I said that this is the Euler-Lagrange equation of this, it's not completely true. Because when you are not looking for a minimum, and you just look at the Euler-Lagrange equation of this, you get a much less precise equation. The equation you get is a commutator equal to 0. So gamma should commute with the mean field operator associated with gamma. That's the Euler-Lagrange equation, nothing else. Now, you want something more, you want to avoid negative energy states. So you're going, and also you don't want your wave functions to have an energy larger than the rest mass of the electron. And so you impose, in addition to this commutator being equal to 0, you impose that gamma j be a projector projecting on a subspace of the spectral subspace of d gamma associated with the interval 0, 1. So you want really your energies to be between 0 and 1, which is mc squared. Okay, and so in fact, if you put all these constraints, you can prove the existence of solutions of this equation, commutator gamma d gamma equals 0. You can even prove the existence of infinitely many of them. And of course, one of them has the smallest possible energy. And you can try to define this as a ground state. So this is something which was done by Maria Esteban and myself in 1909, but under very restrictive conditions, and then by Eric Paturel in very, very general case. And something we could add, we could study the non-relativistic limit of the solutions for the solutions of this problem that we had found. And we could prove that when the velocity of light is very large, which is like saying that alpha, the fine structure constant, is extremely small, then you have a simple characterization of the solution with minimal energy. And in fact, it's a minimum of the Dirac-Fock energy, but under constraints. The constraints, so the first line of constraint is just the usual one, okay? You should have a projector of trace n. But then the second line means that gamma should live in the positive spectral space of d gamma, okay? Which is this condition that this inequality gamma less or equal to the spectral projector of interval 0, 1 associated with d gamma. Now, this last constraint, this last line of the slide, is a very nonlinear constraint. And so we were not able to prove that the solution we had found were solution of this minimization problem when alpha is not very small. And in fact, we had no estimate on the smallness of alpha. And that's problematic because alpha in reality is not infinitely small. It's 1/137, nothing else. Okay, so the question was, how do you improve this? So a first result in that direction is due to Huber and Siedentop in 2007. But they only looked at the special case of closed shell atoms. So how are they called in chemistry? Noble gases. Okay? So in that case, of course, you can impose some radial symmetry, and you can try to make sense of the self-consistent equation independently of any variational interpretation. And you can try to solve it as a fixed point problem by checking some contraction assumption. So okay, so you have to check that the map which to gamma associates the spectral projector, so the Aufbau projector on the first n eigenstates of the mean field operator d gamma, you have to check that this map is a contraction. And of course, this is so. In quantum chemistry, I know that the iteration, the root and iteration is quite commonly used. But if you want to make sense of it mathematically, if you want to check that you have a contraction and so that you have convergence, it's quite hard. And in fact, they could only do it under very restricted conditions, but explicit, which is already better than what we had. We had nothing explicit. Okay, so they have something explicit, but so they have a constraint on the fine structure constant alpha. Okay, and so they impose that alpha should be less or equal to a certain alpha naught of nz. But unfortunately, so they have a nice curve with this alpha naught as a function of nz, and they find that it's never better than 3 times 10 to the minus 3, and it's only like this in a quite narrow region. Okay, for n equal 2 and z between 60 and 80. So and also it only works for closed shells, for noble gases. Closed shell, noble gases. So there was some room for improvement, and that's what I tried to do. So here is the result I obtained. In fact, the idea was to the idea behind this slide, and this is in fact the main result I want to present today. The idea is to do the analog for Dirac-Fock of Lieb's principle. So I remind you what Lieb's principle is. Lieb's principle is for non-relativistic Hartree-Fock, you relax the condition that gamma should be a projector of rank n, and instead you take it in a convex set. Okay, gamma square less or equal to gamma. Okay, and then you hope that the minimizer will saturate the constraint. So I tried to do the same for Dirac, but you run into a problem because you want also your wave functions to live in the orthogonal of the Dirac sea. So you see the constraint here in the middle of the slide. In fact, you don't impose that gamma square should be equal to gamma, but your self-adjoint matrix gamma should be larger or equal to 0 and less or equal to the positive spectral projector of d gamma. And now this is no longer a convex constraint. It's a non-convex constraint. Okay? But the good news is that I was able to prove, even if it's a non-convex constraint, I'm able to prove the existence of a minimizer of the Dirac-Fock energy under this constraint. And I can prove that this minimizer satisfies an Euler-Lagrange equation, which is not so bad. It's not exactly what we want, but almost. So I remind you what the correct Euler-Lagrange equation should be. So gamma should be a spectral projector associated with an interval 0 mu, mu being a chemical potential. And here, what I get is that it's almost like that. It's made of a sum, the first term, which is spectral projector on the interval 0, mu, mu excluded. And then you have a correction Q, which is not necessarily a projector, but it's a self-adjoint operator, which is between 0 and the spectral projector on the eigenvalue mu. And the trace of the minimizer is n. Okay, so this last thing, this Q here, means that when you look at the last level, so the last occupied level, maybe it's not completely occupied, maybe it's partially occupied, and so you have a statistical mixture of states, of electronic states, partially occupying it. Okay, and now I have explicit constraints so that the method works. That's the awful thing that is written here, condition 2. But now if you go to numerics, you find that condition 2, well, of course, it's mathematics, so probably it's not optimal. It works. So let's say in 2 cases where I did the computation, for n equal 2 and z between 2 and 63, or for n equals z, neutral atoms, and then z should be at most 22. So let me give you just a brief idea of the proof. So first, in order to prove this existence result, what you have to do is to deal with the nonlinear constraint 0 less or equal to gamma less or equal to the positive spectral projector of d gamma. And the way it is done is to build what I call a retraction. So first, I call capital G of n the set of density matrices. So it's a convex set, this G of n. These density matrices are between 0 and the identity. So they have eigenvalues between 0 and 1. And its trace is at most, their trace is at most n. Okay? And then for any gamma in this G of n, one can define the positive spectral projector of the mean field operator associated with gamma. And then you define G plus of n, which is the set of density matrices that have a range included in the range of P plus gamma. So it's not the self-consistent equation we want to solve, but it's a part of it. It says that gamma is orthogonal, the wave functions in the range of gamma are orthogonal to the Dirac-C in the field generated by gamma. Okay, so it's a nonlinear condition. So now this G plus of n is no longer convex. But what I can do, I can find a mapping theta, which to any point in the neighborhood of G plus associates another point in G plus. And this map theta is such that if you start from a point in G plus, then theta of that point is itself. So G plus is made of fixed points of that mapping. And now this mapping, this retraction of a neighborhood of G plus onto G plus is obtained just by an iterative procedure. Okay? So you start from gamma 0 in this neighborhood, and you define a sequence by saying that gamma n plus 1 is just gamma n sandwiched between two copies of the projector associated with gamma n. Okay, so this is a contraction. Well, you can prove that this sequence has contraction properties, and you can prove that it converges at a geometrical rate under, of course, this awful assumption 2. Okay. Let me show you a picture. Sorry. Yeah. So here you see this is okay. My notations are a little bit different because it's a handwritten picture I made before the slides. But this is Gn. What I call gamma n here is Gn. So it's a convex set of all possible matrices, and Gn plus, so gamma n plus, is this non-convex set which is represented by a line, and theta is a map which to any point associates in any point in Gn associates the points in Gn plus. Okay, so now how do you use this retraction? Well, let us admit it needs some functional analysis, but one can prove that the Dirac-Fock energy has a minimizer on Gn plus. Once you found it, call it gamma bar. We are going to prove that it satisfies the Euler-Lagrange equation I am interested in, okay, which is this one. It's number 3. Okay, and I don't know why it's written 5 here, but it meant so 5 has to be understood as 3 here. Okay, so assume it does not satisfy the Euler-Lagrange equation. Then you define the Aufbau projector on the n first positive eigenvalue and your eigenvectors, so associated with the n first positive eigenvalues of the mean field operator associated with d gamma. And then you construct a new density matrix by taking a convex combination between the minimizer gamma bar and this Aufbau gamma prime, with here an S0, which is optimal in the following sense. So you take this convex combination, you apply theta to it. Theta is this retraction I was talking about. And S0 is the minimizer on the interval 0, 1 of the energy, the Dirac-Fock energy of theta of this convex combination. Okay? And now it's, after some computation, you check that if the Euler-Lagrange equation is not satisfied by gamma bar, then this gamma tilde does better. The energy decreases. It's smaller for gamma tilde than for gamma bar. Okay, and so of course it's a contradiction. It says that gamma bar was not a minimizer, and so by contradiction, one proves that the minimizer, which is found by some functional analysis tools, solves the Euler-Lagrange equation. Now, if I think I'm almost done, but if I have 2 more minutes, I can explain that, in fact, this proof translates immediately into an algorithm. And this algorithm is just a relativistic version of the ODA algorithm of Cances-Lebris, which was introduced for non-relativistic Hartree-Fock. So the algorithm is very simple to describe. Suppose that at step n, you have found a density matrix gamma n, which approximates the problem, ground state problem you want to solve. So this gamma n is in G plus of n, so it's orthogonal to its own Dirac C. And then you build the Aufbau projector associated with d gamma n. Oh, sorry. Oh. Okay, and then you define gamma n plus 1 as theta of the optimum of the optimal point on the segment between gamma n and gn. Okay, same thing I did for the proof, but now you do it in an iteration. And then it's not hard to check. It's almost a tautology, because here you have a minimizer, so the energy of the minimum of the minimizer is smaller than the energy for S equal 0. Okay, and here this gamma p is the gamma n. Sorry, and so you find that you get a sequence with a decreasing energy, and also you can check that gamma n plus 1 minus gamma n decreases in some convenient norm. and so you can prove that the distance between gamma n and the set of ground state converges to 0. Okay, so this algorithm is not very difficult to implement, well, except that of course you have to do complicated work before, if you are not an expert in relativistic quantum mechanics, which we are not. But it was done by Maxime Chupin, Guillaume Legendre, and Antoine Levitt, and so now we are testing it. Yes. I cannot show you nice pictures because this is work in progress. And the last thing I wanted to talk about, just to justify the title, but I see it's really late. So that's a picture, okay, for the iteration. So you start with gamma n, you have gn, which is on the boundary, and then on the segment here, you project the segment on gamma n plus, and you look for an optimal point. Okay, so the last thing I wanted to talk about is the very recent work, which is an extension of Dirac-Fock to crystals. Essentially, you look you look at crystal, let's say, with cubic cell and with nuclei located in the center of each cell. Well, you look for an electronic state, multi-electronic state, which is given by a periodic density matrix, which can be split into density matrices on each space of block functions. Well, so you get a no full energy. I don't even want to comment this, okay? But that's the Dirac-Fock energy you get, okay, with for this periodic system. And well, you can do essentially the same that I did in the molecular case, except that it's much more technical. And so we can prove the existence of a minimizer of the Dirac-Fock energy under constraints that generalize Lieb's constraints, but of course with this highly nonlinear part here, saying that gamma should be orthogonal to its Dirac C. Okay, and so we get essentially the same result. And let me say that before that we had tried to study this problem by using ideas coming from what we had done earlier with Maria Esteban and what Eric Paturel had done. And so this kind of approach, critical point approach, it didn't work because the functional analysis was too hard. And in fact, the problem was it's not so easy. So when you look at it from a point of view of critical points, you have to look at this Euler-Lagrange equation, this commutator equal to 0, and it has bad properties from the functional analytic viewpoint. If you mix this with block functions, okay? So that's really because of this minimization problem here that the problem could be solved. Okay, so, well, I thank you.